Hello, this presentation will cover the use of Bezier curves for forming circular arcs. For this, it will be required that we use homogeneous representations for control points and that the curve formula, the Q of U value, is a homogeneous representation of a point. It's not possible to get circular arcs using Bezier curves otherwise. We're going to concentrate primarily on degree 2 Bezier curves because they're perfectly good for this purpose and simpler to work with than degree 3. It is easy to convert a degree 2 Bezier curve to a degree 3 Bezier curve if needed. So we're going to use degree 2 Bezier curves for circular arcs with control points that are homogeneous representations of points in R2. So let's start with an example, and these sort of our canonical base example that always works. I'm going to draw a semicircle with, here's the origin, is the dot in the middle. We're talking about the unit circle here. So here's the point 0, minus 1 in R2, and the point 0, 1 in R2, and it's a unit circle, and we're going to use homogeneous representations of these control points. So P0 is going to be 0, 1, 1, and P2 will be 0, minus 1, 1, and these will be the first and the last control point of a degree 2 Bezier curve. For the middle point, the P1 point, it needs to be, in general, it should be out that ways in such a way that the middle control point forms with P0 to P1. That line segment should be tangent to the top of the circle, and likewise the line from P2 to P1 should be tangent to the bottom of the circle, just because Bezier curves always start off tangent to the control polygon and end up tangent to the control polygon. Well, these two tangent lines are parallel, so they don't meet anywhere in the plane, but they do meet at a point at infinity. So out here, P1 will be the point 1, 0, 0. So we can sort of think of these lines as, I have to draw them curved on the board because my board is only finite length, but if it was infinite length, they could go out straight and they could meet at this point at infinity. So our control points for the curve are P0 equals 0, 1, 1. P1 equals 1, 0, 0, and P2 equals 0, minus 1, 1. So the middle point, again, is a point at infinity because its W component is 0. So the claim here is that for 0 less than or equal to u less than or equal to 1, the values Q of u are homogeneous representations of points that trace out the unit circle or the unit semicircle as shown in the picture above. So the traces out the right half portion of the circle. So I'll prove this for you in a moment, but let's unpack this just a little bit here. First of all, recall that Q of u as a degree 2 curve, it's equal to 1 minus u squared times P0 plus 2 times u times 1 minus u. times P1 plus u squared times P2. So, for example, as an example of the claim, this is with u equals 1/2. Our q of 1/2 is equal to 1 minus u squared times P0, so that's 1/4 times P0 plus 2 times u times 1 minus u. Since u is 1/2, that's all equal to 1/2 plus 1/2 P1 plus u squared times P2, so that's 1/2 squared times P2 plus 1/4 times P2. So if we add this up, I've got 1/4 times P0, 1/2 times P1, and 1/4 times P2. And when you work that out, that ends up being 1/2, 0, 1/2. So that's the value of q as a triple, as a 3-vector, and it's the homogeneous representation of what point? Well, we divide by the w value, the 1/2, and we find out that it's the representation of the point 1, 0. So this is, which represents 1, 0 in R2. So 1, 0 is the point, of course, right here at the right edge of the semicircle. So the claim is saying that this kind of thing works for all values of u. At u equals 0, we represent the point P0, of course. We get the value P0, which represents 0, 1. At u equals 1/2, we just showed we get the value, the triple 1/2, 0, 1/2 that represents 1, 0. And at u equals 1, we get the triple 0 minus 1, 1, namely P2, which of course represents 0 minus 1. And we claim that this holds in general. And I'll show that on the next board. So for the proof of the claim, we just expand the definition of q of u to get started. So q of u is 1 minus u squared P0 plus 2u 1 minus u times P1 plus u squared times P2. So to write this out in terms of x, y, z components, we've got the only place where there's an x value that's non-zero is in P1. So this is 2u times 1 minus u, comma, and this is the first component of the 3-tuple for q of u. We've got a 1 and a 0 and a minus 1 as the y components of P0, P1, and P2. So we get 1 minus u squared minus u squared as the y component. And then finally we've got 1, 0, and 1 as the w component. So we get 1 minus u squared plus u squared as the w component. So this is what q of u is equal to as a function of u. And I can call this x of u. I can call this y of u. And I'll call this w of u. So in other words, we have that q of u is the triple x of u, y of u, w of u, and of course this represents the point x of u over w of u, y of u over w of u in R2, because as a homogeneous representation with x, y, w components, we just divide by the w component to get the point represented in R2. So we need to show that this lies on the unit circle. So we need that this point lies on a unit circle, so in particular we need x of u over w of u squared plus y of u over W of u squared equals 1, so that we're representing a point at distance 1 from the origin. We need to show more things too, namely that we're always on the right side of the circle instead of the left side, but that's easy to show just by checking the signs of these functions for u between 0 and 1. So, continuing with this part of the proof though, for this we need to show that x of u squared plus y of u squared equals w of u squared. But we've got these formulas for x and y and w. If we just substitute those formulas in and simplify, we find out that it's true. And thus this equality is easy to check. And that proves the claim. I'll let you check the equality on your own. So I've given you a degree 2 Bezier curve for the semicircle. It's also possible to get a degree 3 Bezier curve. To check that it works is a little bit more complex because there's more terms involved, but it's equally straightforward. You can also get it by a technique known as degree elevation or degree raising. I'm not going to do that general technique, but I'll just show you the example of how it applies to this. So the same semicircle as a degree 3 Bezier curve. It's the following. So here's our x-axis, here's our y-axis, here's the same semicircle I've got pictured up there. The first control point, P0, it's still 0, 1, 1. The last point is now P3, because a degree 3 Bezier curve has control points P0, P1, P2, and P3. So P3 is the same as the old P2. It's 0, minus 1, 1. And now the point at infinity is no longer used. Instead, we have two control points, P1 and P2. And those sit, as it were, right here. P1 is equal to 2/3, 1/3, 1/3. In other words, it's 2, 1 in R2 with weight 1/3. So the control point is 2/3, 1/3, 1/3, but it will often be reported as being the point 2, 1 because this represents the point 2, 1 with weight 1/3 because the W value is 1/3. And then P2 is 2/3, negative 1/3, 1/3, i.e. 2 minus 1 with weight 1/3. So the control polygon is here, and it's straightforward to check that the degree 3 Bezier curve defined with these 4 control points is exactly the same as the degree 2 Bezier curve defined with these 2 control points, in the sense of Q of u for this curve is always exactly equal to Q of u for this curve. But for the rest of this presentation, we'll just talk about degree 2 Bezier curves. I want to talk next about translated and rescaled versions of this circle and show how to get control points for circles in other positions than just the standard position of a unit circle centered at the origin. Let me start by redrawing this up in the corner out of the way a little bit. So now I've redrawn the semicircle up in the corner of the board to give me more room. And the rest of the board, we want to talk about different versions of this semicircle under translations and scalings and so forth. We'll see the general principle very quickly. So let's try an example of the translated semicircle. So I'm going to do still the unit 1 semicircle. And I'm going to move it up 1 unit so that here's the origin. Here's the point 0, 2. Here's the point 0, 1. And it's a semicircle of radius 1. And we'd like to find the control points for this as a degree 2 Bezier curve. And we want the Bezier curve, of course, to trace out this translated semicircle. Well, P0 has to be the starting place. So it seems pretty clear that P0 ought to be 0, 2, 1, because it's starting at the point 0, 2. This previous curve started at the point 0, 1. So it seems like P0 ought to be 0, 2, 1. And then it likewise seems like P2 ought to be 0, 0, 1, because the point 0 minus 1 has been moved up to 0, 0, and we keep the weight the same. And P1, it's a point at infinity still. That seems pretty clear. And how do we find this point at infinity? We follow the x-axis out to the point at infinity, right? So here we're sort of following this central line of the circle out until it gets to a point at infinity, or more to the point, we're following the top tangent line and the bottom tangent line out until they reach a point at infinity. And which point at infinity do they reach? They still reach the same P1 equals 1, 0, 0. Because as you will recall from an earlier video, parallel lines all share a common point at infinity. So P1 should be 1, 0, 0. So this is the intuition. You may start to worry about this intuition, is it correct? You can easily plug in these numbers and find out it's correct, but let's try to be a little more scientific and find some method for doing this rather than just some guesswork like I just did here. So to be more scientific, or to get a method or formula, the translation matrix that acted on the semicircle is 1, 0, 0, 0, 1, 0, 0, 1, 1. Because this is a 3 by 3 matrix that acts on homogeneous coordinates in R2. So this acts on homogeneous coordinates in R2. And we'll just take this, let's call this M, give it a nice name. And we would just want to form, so we want the curve, so we want the curve to be transformed by M. And for this, it's enough to transform the control points. We have that M times P0, 0, that's the 0, 1, 1, is equal to, well, you've got 0, 1, 1 times the top row, inner product of the top row is 0, inner product of the second row is 2, inner product of the third row is 1. So 0, 2, 1 is what M sends P0 to. M of 1, 0, 0, that's M times P1. Well, that's still 1, 0, 0. So P1, the new P1, is just is M times the old P1, and likewise M times 0 minus 1, 1 is 0, 0, 1. Again, you can take the column vector 0, minus 1, 1 and inner product it with the 3 rows, and you get 0, 0, 1, which is our new P2. So these are the control points for the degree 2 Bezier curve that traces out the semicircle as translated here. And the fact this works depends on an old theorem from a previous video, which stated that affine combinations are preserved under affine transformations. So M is an affine transformation because it's a translation. And the computation of Q of U for a Bezier curve is an affine combination because the coefficients on P0, P1, and P2 add up to 1. So this tells us that if you move the control points around according to M, that also moves the points on the curve around according to M. So if we want to get the translated circle, it's enough to translate the control points. Now we'll try a scaled circle. I'm just going to uniformly scale the semicircle by the factor 2. So now our semicircle is still centered at the origin, but it's got radius 2. So the semicircle starts at 0, 2, ends at 0, minus 2, and for this, we use control points P0 equals 0, 2, 1, P1 equals 2, 0, 0, not 1, 0, 0, and P2 equals 0, minus 2, 1. So the surprise here might be that the point at infinity changed. And again, remember that we're looking for, we can tell which direction it is out to the point of infinity, because if we follow the tangent lines from the beginning and ending of the semicircle, they meet at a point of infinity. Now 2, 0, 0 is the same point as it were as 1, 0, 0, but expressed differently. It's a different representation for the same point of infinity. And how did we know to use this one instead of the original P1? Well, the rationale here is that we have the scaling matrix. We have M, our new scaling matrix, is 2, 0, 0, 0, 2, 0, 0, 0, 1. You recall this does no translation. It keeps the origin at place, and the 2 by 2 part scales both the x and the y by the factor 2. And then M, applied to the original P0, 0, 1, 1, is equal to 0, 2, 1. And M applied to the point at infinity on the original curve, 1, 0, 0, is 2, 0, 0. And M applied to the third control point, 0, minus 1, 1, is 0, minus 2, 1. And this gives us the claimed control points for the scaled semicircle. For our third example, let's try an ellipse or semi-ellipse that's been translated as well. So translated semi-ellipse. So here's my x-axis. The ellipse will have major radius 2. Make that a little longer. And minor radius 1, so it's going to look like this. Here's half the ellipse, and the other half of the ellipse is over here. Okay, so this is an ellipse. And this is the midpoint is 0, 2. The starting point of the half ellipse is here at 0, 3. The ending half of the ellipse is here at 0, 1. This point here out at the right end is 2, 2. And we'd like to get a degree 2 Bezier curve that traces out this ellipse. So for this, we're going to use m equals what? Well, we're going to scale by a factor 2. We're going to take the semicircle and scale by a factor 2 in the x direction. We're going to not do any scaling in the y direction, so it'll stay the same size in the y direction. And we're going to translate it up by 2, so the center of the ellipse is at 0, 2 instead of 0, 0. And now we can compute m applied to the original P0, 0, 1, 1, is equal to 0, 3, 1. And m applied to the point infinity, P1, which was 1, 0, 0, turns out to be 2, 0, 0. So by scaling in the x direction, we also change the middle control point by the same factor. And then m applied to the original P2, 0, minus 1, 1, is equal to 0, 1, 1. Namely, the point translated up by 2. So this is the degree 2 Bezier curve with control points as given below: 0, 3, 1, 2, 0, 0, 0, 1, 1. So this general method works for any affine translation. These were particularly simple ones. But notice, one thing to notice here is that the scaling in the x direction is what controlled the point at infinity. Had we scaled also in the y direction, it would have made no difference to the point at infinity. The point at infinity only reflects the scaling in the x direction. But for any other affine transformation, the same principle works. If you wanted to rotate the semicircle, you would just take m to be a rotation matrix. If you wanted to do some shearing transformation, you could just take m to be the shearing transformation, and so forth. To finish with one final example, I want to look at a semicircle that traces out only a quarter of a circle. So far, all of our examples have used a point at infinity, and they were forced to use a point at infinity because when you took the tangent lines at the beginning and the ending of the semicircle, they met at a point at infinity. So the center control point had to be point at infinity for a Bezier curve of degree 2. But we can also work with smaller semicircles. So for instance, here's x-axis, y-axis, and let's take semicircle of radius 1. We're centered at the origin, and here's the point 0, 1 is where the semicircle starts. And here's the point 1, 0 where the semicircle ends, and it's a semicircle of radius 1. And we want to find a Bezier curve that traces out this semicircle. So we're going to use P0 equals 0, 1, 1 as the starting point. P2 equals 1, 0, 1 as the ending point. And the middle point, by our rationale that the middle control point has to lie on the two tangent lines to the beginning and ending of the curve, the point should be here. It turns out that P1 should be square root of 2 over 2, square root of 2 over 2, square root of 2 over 2, i.e. it's 1, 1 with weight square root of 2 over 2. And I'm not going to do the derivation, but you can check that this actually gives you a semicircle, that the weight has been chosen appropriately, and that when you do the computations, the Q of U exactly traces out this first quadrant of the semicircle, starting at P0, starting at 0, 1, and ending at 1, 0. And that's all for this presentation. Thank you very much.